The date is July 17th, 1981. A hotel lobby in Kansas City is packed with more than 1,600 people. They're dancing. They're drinking. They're watching a tea dance contest 4 stories below 3 suspended walkways hanging in midair like bridges in the sky. Nobody looks up. Nobody has a reason to. And in less than 3 seconds, that decision will cost more than 100 lives. This is the story of a single number, changed on a piece of paper, months before the party started. A change so small that the man who approved it probably signed off in under a minute. He never did the math again. And that missing math turned a hotel atrium into the deadliest structural collapse in American history until 9/11. Let's go back to the beginning, because the real disaster didn't happen on July 17th. It happened at a drafting table more than a year earlier. Act 1, the prelude. Kansas City wanted a symbol. In the late 1970s, the city was rebuilding its downtown, and the Hyatt Regency was supposed to be the crown jewel. A 33-story hotel tower connected to a massive atrium lobby, the kind of space where you walk in and your neck cranes back on instinct. Glass ceiling, open air, and hanging inside that open air. 3 walkways on the 2nd, 3rd, and 4th floors, connecting the hotel tower to the parking garage building next door. The design called for these walkways to be suspended, literally hanging from the ceiling on steel rods, like a swing set bolted to the sky instead of a tree branch. The 4th floor walkway would hang from the roof. The 2nd floor walkway would hang directly underneath the 4th floor walkway, sharing the same rods, one on top of the other, connected through the same vertical lines of steel. Think of it like 2 shelves stacked on a single pole. If both shelves share one pole and that pole is only strong enough for 1 shelf's worth of weight, stacking a 2nd shelf on it doesn't double the strain evenly. It creates a bottleneck, and bottlenecks in engineering don't fail gently, they fail all at once. The original design, drawn up by the structural engineering firm Jack D. Gillum and Associates, called for a single, continuous steel rod running from the ceiling all the way down through both walkways to an anchor at the bottom. 1 rod, 2 floors, 1 connection point at each level, held by a nut and a washer. On paper, this was already going to be tight. The load was significant, but the calculations, if done correctly for this single-rod design, showed it could work. Barely. It would meet the Kansas City building code, but just meet it. No real margin, no cushion for a packed lobby of dancing bodies on a summer night. But here's the twist. That original design was never actually built. Act 2, the invisible flaw. Somewhere between the drafting table and the construction site, a problem came up. And it wasn't a problem with the engineering. It was a problem with construction logistics. To build the original single-rod design, workers would have needed to thread 1 continuous rod, running from the ceiling anchor all the way down through both walkways, and then twist a nut onto the bottom of that rod to hold the 2nd floor walkway in place. That meant the entire rod, the full length running through 2 floors, would need to have threads cut into it, or the whole rod would need to be turned like a giant screw to tighten that lower nut. On a construction site, spinning a rod that runs through 2 structural floors is not simple. It's clumsy, slow, and genuinely dangerous for the workers doing it. So the steel fabricator, Haven Steel Company, proposed a fix. Instead of 1 continuous rod running through both walkways, why not use 2 separate rods? The upper rod would run from the ceiling down to the 4th floor walkway. Then a 2nd, shorter rod would run from that same connection point on the 4th floor down to the 2nd floor walkway below it. It sounds harmless. It sounds like a shortcut that makes the build easier without changing anything about how the structure works. That assumption is exactly where more than 100 people's fate was decided. Here's the part that matters. In the original single-rod design, the connection point on the 4th floor only had to support the weight of the 4th floor walkway itself. The 2nd floor walkway's weight passed straight through that connection, carried further down by the same continuous rod, all the way to the anchor point at the very bottom. But in the new 2-rod design, that 4th floor connection point now had to support 2 things at once: the weight of the 4th floor walkway and the entire weight of the 2nd floor walkway hanging below it. Every ounce of load that used to pass straight through was now stopping and stacking directly onto a single box beam and a single nut on the 4th floor. In simple terms, imagine holding a rope with 2 buckets tied to it, one at your hand and one further down the same rope. Now imagine instead tying the 2nd bucket's rope directly onto the 1st bucket's handle. The 1st bucket's handle is now carrying double the weight it was ever designed for. That's exactly what happened, except the handle here was a welded box beam, and the load wasn't buckets of water. It was hundreds of human beings. This change was sent to the engineering firm for review, and this is the moment the entire disaster hinges on. The change was approved. Fast, informally, without redoing the load calculations for that fourth-floor connection point under its new doubled burden. Nobody sat down and asked the simple question: does this connection point, now carrying twice the load it was designed for, still meet code? If someone had run that number, they would have found the connection was only capable of supporting around 30% of the load required by code. Not close to failing. Already failing mathematically the day it was built, and for over a year it held. Because static weight and empty walkway with nobody on it was nowhere near its limit. The flaw was invisible, no cracks. No warning signs, no sagging. Just steel sitting quietly above thousands of hotel guests, undersized in a way nobody could see with their eyes. Act 3, the sudden collapse. Now to July 17, 1981. The Hyatt Regency is hosting a weekly tea dance in its atrium lobby. Big band music, a packed floor. And on the walkways above, hotel guests are gathering to watch the party from a bird's eye view, exactly the kind of casual crowding the space was built to invite. At the fatal moment, dozens of people are standing on the second and fourth floor walkways. The dead weight of the structure, plus the live weight of the crowd, finally pushes past that 30% threshold. The welded box beam connections on the fourth floor, the ones nobody recalculated, begin to give way. Witnesses would later describe hearing a loud crack, then a series of popping sounds like gunfire as the connections failed one after another down the length of the walkway. There was no slow bending, no time to run. The fourth-floor walkway broke free from its rods and dropped directly onto the second-floor walkway beneath it, which was already at its own breaking point. Both walkways together, along with everyone standing on them, crashed down onto the crowded lobby floor below. In under 5 seconds, more than 65 tons of steel and concrete fell 4 stories onto a dance floor filled with people who had no warning at all. The sound was described by survivors as an explosion. A cloud of dust and debris filled the atrium, and then silence followed by screaming. 114 people died that night, either instantly or from injuries in the hours that followed. More than 200 others were injured, some pinned under slabs of concrete and twisted steel for hours as emergency crews worked to cut them free. Kansas City firefighters would later call it the worst rescue operation they had ever responded to, made harder by the fact that the debris itself was structurally unstable, threatening to shift and crush both victims and rescuers. This remained the deadliest structural collapse in United States history for 2 full decades, until the towers fell on September 11, 2001. Act 4, the aftermath and investigation. In the days after, investigators from the National Bureau of Standards descended on the wreckage, and what they found, once they traced the design change back through paperwork and shop drawings, was almost unbearably simple. The failure wasn't caused by cheap materials. It wasn't caused by a natural disaster or an unforeseeable accident. It was caused by a design modification that doubled the load on a single connection point, approved without anyone redoing the math. The investigation exposed a deeper problem in how the project was managed. The engineering firm had a practice of approving shop drawings, the fabricator's construction blueprints, without conducting full independent engineering reviews. The assumption was that shop drawings were just construction details, not real engineering decisions. But in this case, a construction detail was an engineering decision. The line between the two had quietly disappeared, and nobody was watching for it. 2 of the engineers involved, Jack Gillum and Daniel Duncan, had their professional engineering licenses revoked in the state of Missouri. This became one of the most cited case studies in the history of structural engineering ethics, taught in engineering schools around the world to this day. Students are shown the 2 rod designs side by side, one carrying its load straight through, one stacking it onto a single failure point, and asked to spot the difference. Most can't, not at first glance. That's the point of the lesson. The disaster directly reshaped how the engineering profession operates. It led to stricter requirements for structural review of shop drawings, clearer legal definitions of an engineer's responsibility during construction, and updated codes for how load paths must be documented and verified any time a design changes, no matter how small that change appears on paper. The truly disturbing part of this story isn't the collapse itself. It's how ordinary the mistake looks. Nobody set out to build something dangerous. Nobody ignored an obvious warning. A shortcut got proposed to make construction easier. It got approved in what was probably a routine, forgettable moment in someone's workday. And the gap between "this seems fine" and "did we verify this is fine" swallowed more than 100 lives. Every bridge you cross, every walkway you stand on, every parking garage you drive through carries an invisible promise that someone checked the math, and then checked it again. The Hyatt Regency walkways prove that promise can break silently, for over a year, before anyone finds out the hard way. If you want more deep dives into the hidden engineering failures and forgotten disasters that changed the rules of the modern world, subscribe to the channel. There's more history like this waiting for you.